Hello everyone. Sorry, let's get back to where we left off. So again, the goal is to calculate what the pressure is that is exerted by the fluid on the top surface, right? So again, what we did was solve the lubrication approximation, get an estimate for the velocity Vx, Vy, and then from that you can also calculate the pressure drop. Please read the book. It shows that the pressure can be is goes as mu L over U divided by h squared, right? So the dynamic pressure is pretty significant because it goes as 1 over h squared. Then what you can do is now, how do you calculate the forces on surfaces, right? So basically, you have the top surface. Let's say the normal vector is always normal to the surface and pointing outwards, right? How do you calculate the force on a surface? To get the force on the surface, first you calculate what the stress vector is. Stress vector is n dot sigma, where sigma is a stress tensor, which is what is given here, right? And then again, this goes back to the equations for the stresses. So n dot sigma. So how do you calculate that? But before that, you need to get to an expression for the unit normal to a surface, which is what is given here, right? So how do they get to this expression, right? So please don't blindly accept when things are given in the book, right? First, see if you can derive it yourself and if it makes sense, right? So how do you do that? I mean, look, basically, I mean, look at that. I mean, this is a unit normal to the surface. So I draw a tangent to the surface, right? And say this is theta, right? So what is tan theta? Tan theta is nothing but dh over dx, right? So all I need to do is I need to resolve the normal vector into the x direction and into the y direction. So my normal vector is nothing but I mean I can take it as nothing but cos theta times ex, and minus, so when I take the normal vector to the y direction, it points downwards. So minus sorry, it's sine theta times ex minus cos theta times ey. I mean, look, it's angles, right? I mean, so if this is so this is 90 minus theta, so sine theta ex minus cos theta ey. So and which is basically the expression here. So that is right. So yes, I mean, we can work it out a little bit more in class as well. So now, once you get to the normal vector, right? So what you need to do is you need to do n dot sigma. N dot sigma is nothing but n dot sigma is nothing but the stress vector S. So look at this. So when you do n dot sigma, is nothing but nx ny times the stress tensor. So is nx times sigma xx and ny times sigma yx, right? So dh over dx times sigma xx minus sigma yx. And what is sigma? Sigma is nothing but sigma is your stress tensor, right? Sigma is what? Minus p times delta plus tau. Okay, so basically, I mean, look, which is what is given here. So sigma xx is nothing but minus p plus tau xx, right? So again, I mean, look, I think you just have to put together what you have learned a little bit before, right? So you can get sx, you can get sy. Now there are a bunch of terms in here, right? So basically, but what this is saying is you can neglect now certain terms. Like in this first expression, you can neglect tau xx. In the second expression, actually, you can neglect this and you can neglect this. The question is how? So you can do that by simple order of magnitude scaling. So basically, look, what did we say, right? I mean, let's look at the term tau xx, right? So what is tau xx? Tau xx is mu times dou vx over dou x. Okay, so this is nothing but this goes to the order of u divided by L. So L is large, right? So which means you neglect tau xx. Simple. Same thing now. So, okay, so that's one term. Now dH over dx times tau xy, right? How do you do that? Dh over dx times tau xy, right? So this is nothing but, this is of the order of dH over dx is nothing but h over L. Tau xy is mu times dou Ex over dou y. Y is nothing but h, right? Again, mu u over L. L is large, so neglect this. Look at P. Compared to P, P goes as, I mean, we just did that, right? What did we do? P mu L over u over h squared. And now compared to P is, so dH over dx times tau xy goes as mu u over L. Mu u over L divided by h squared. Look at that h squared at the bottom. So P is much bigger than dH over dx times tau xy. So basically, so you can neglect dH over dx times tau xy compared to P. Again, what is tau yy? Tau yy is mu times dou vy over dou y, right? V is anyway, vy is small, okay? So mu times vy, I mean, let's say this is u divided by y is h, but then P goes as 1 over h squared. So again, this is the dominant term. So basically you can get Sx, you can get Sy, which are the stress vectors. Stress vector is nothing but the force per unit area. Now, how do you get the force? Now you're talking of the top surface, right? I mean, look at that again. This value is G, right? The value of this length is G. The width is W. So force is Sx times G times W. This is the force per unit width, right? So the G cancels, right? And then that's why you get this expression. Integrate with respect to x. X can go from x1 to x2 along the top surface, and you can get fx and fy. So this is extremely powerful. I mean, lubrication theory gives you really, by starting from simple approximations and constraints, you can calculate a lot of very powerful quantities. I mean, another good source is also Dr. Hallinen's notes. I mean, which is, he just works it out in the book. I mean, it's the same thing. We can do it in class too. This is what I was planning to do. I mean, we are like two classes behind because of the cancellations, right? So, I mean, look, this is the same problem. So again, you solve the Navier-Stokes, simplified Navier-Stokes, right? With the lubrication approximation, you can get to the expressions for Vx. At the top surface, the velocity is 0. At the bottom surface, it's, I mean, the book says U, he uses sigma. Now you can calculate what the volumetric flow rate is, rearrange, you can get dp over dx. Now you can get Vx as a function of y. Then you can calculate dou Vx over dou y, obviously, because, that tells you what the forces are going to be. You can also, I mean, you can calculate a bunch of other things. You can calculate what the pressure drop is. Once you get to the pressure drop, listen, I think, obviously it's going to play, and then the book shows that my pressure drop goes as mu u L over h squared, right? So once you calculate the quantities, you can calculate the force. Force is nothing but stress acting on the surface multiplied by the area. So what is stress? Stress is nothing but n times sigma. You can, this is some math. You can derive what the normal vector is going to be. Once you get to the normal vector, right? I mean, what is this? Take the dot product of n with sigma. You get to the following expressions. And then now you can use order of magnitude estimates to cross out terms. For example, dou Vx over dou x is what? Is nothing but, right? I mean, you can do such things, right? And then you can cross out terms, and then you can calculate what the forces are going to be. So yes, please, I think it's good that you have to work through the math, but again, this is nothing different than the Navier-Stokes that you have done before. So I would say, please spend time, work through the math, do it yourself, make sure you get all the steps right, and then and then think through things, right? Does it make sense?